we're going to start our next unit, which is going to be rotational dynamics, which is basically Newton's laws applied to rotation. So, first, in Newton's laws, we talk about forces. Force is a push or pull trying to make something move. Torque is a twist applied to cause something to revolve. So imagine I'm trying to turn a bolt with a wrench. We're going to apply a force to the handle, and which one would be most effective in turning the bolt, giving the most torque? Well, if I try to push here, it's not going to be very effective. Just from experience, I know the farther out the wrench I push down, the stronger the torque is going to be. And if I look at these three, F3 is useless. It's just pointing straight toward the bolt, so that wouldn't turn it at all. And the one that's going to be most effective is going to be F2. F2 produces the best torque or the largest torque. So, torque is dependent on three things. Torque depends on the amount of force. The harder I push on it, the more it's going to turn. It depends on R, that's the distance from the pivot point. And it's going to depend on theta, the angle between them. And 90 degrees gives the largest torque. So the equation is going to be torque. There's a curly T, it's a Greek letter tau, equals F R sine theta. So here's an example. We have a beam pivoted at the center, so take it right there, and two forces are applied. Okay, we have F1 over here is 40, and F2 over here, which we're going to have to find. First, it says find the torque produced by F1. So for part A, we're going to say torque equals F R sine theta equals 40 newtons times R. R is distance, 6.5 meters. It's a sine 60. When we do that, we'll get a torque of 17.32. Now, units are Newton meters. Torque doesn't have a unit of its own. And we also have to give it a direction. So what I like to do is take a look at this. This is pushing down on this side. That would make the whole thing turn this way around this pivot. So that's clockwise. So I'm going to say that that's a clockwise. Now, part B, okay, what does F2 have to be to keep the beam from rotating? So to make it not rotate, my torques have to cancel. So I can use the same equation. Okay. I have to have the same torque. This time I'm going to be counterclockwise because pushing down on this side is going to make the beam rotate like that. Equals F2. R is 0.3. And when I make a right angle like this, I don't have to worry about the sine theta. Sine 90 is 1. So then find F2 is equal to 57.7 meters. Now, the next page is another example. Okay, we have a static problem here. We're going to do these for a little while. Static problems. There is no movement. So it's not going to turn, so the torques have to cancel. And it actually doesn't move up and down or sideways either, so the forces cancel. So for these problems, we're always going to try to set torques equal to each other and forces equal to each other to make them cancel out. So here's an example. I have a 2-kilogram beam attached to a wall by a single pivot through its center. The beam is in equilibrium by the mass and the forces on the point. So here's one thing we have to be aware of now. I have a 2-kilogram beam. We haven't worried about the mass of the beam before, but now we are. So I know this thing has a mass of 2 kilograms. That's going to give me a force of gravity of 20 newtons right there. Now, I can start out, I have all the information over here on the right side for this tension. There's a string pulling down on this thing. I'm going to do torque is F R sine theta, 60 newtons R is 0.6 meters times sine 30. That's going to give me a torque of 18 Newton meters. And that's trying to make this side go down, so it would turn around clockwise. So that's clockwise. I'm going to show you what happens with this force of gravity. Okay? Torque for this one is F-R sine theta. The torque equals, the force there is 20, but R is 0. Okay? I'm measuring from the pivot point, it's right at the pivot point. So it produces no torque. Torque equals 0 for that. Which is why we never bothered with it before. Now, the last one, over here, remember we have to deal with forces. So the force of gravity on this thing is going to be 10 times the mass. I don't know the mass, so I'll just do this. And then I can set up my equation for the torque for this one. It's going to be F-R sine theta, 10M. R is 2. So that's going to give me 2M for the torque on that side. And that's going to be counterclockwise because it's trying to pull down on this side. So counterclockwise. So now, since I know it's not rotating, I can set the two torques each of each other. So 2M equals 18, M equals 9 kilograms. I'm going to go back up here because I'm going to need this in a second. Remember, the force of gravity on this is 10M. Now that I know that this mass is 9, it's going to be 90. So we're going to use that in a second. So the last part of the problem says, what are the forces on the pivot? We've ignored this before. We haven't had to deal with it a lot. If I think about it, this force is trying to pull down on it, this one's pulling down on it, and this one's pulling down on it. So there has to be a force up at the pivot. So I'm going to call that force on the pivot Y. And then, this force is also pulling it to the right. So there has to be a force to the left. We'll call it LPX. Now, in order for this not to move, you can say something like this. My Y forces have to cancel. Alright? So, looking at my Y forces, I have 90 going down. I have another 20 going down right here. And then, part of this 60 is pulling down. I have to split this up into, say, TX and TY. Because that tension is neither an X or Y, it's a little bit of both. So for TY, it's the opposite of this 30, so I'm going to use sine. So it's going to be 60 sine 30, which is 30. For TX, it's going to be 60 cosine 30, 52.0. So now I have 30 here, and 52 over there. So I have another down force of 30 equals, my only up force is this one right here, the force on the pivot. So F-Y. So if I add those together, I get 140. Force on the pivot Y direction. I can also do my X forces cancel. And I have the following. For my X force, I only have two. I have TX over here, and I have FTX over here. So it's just FTX equals TX. So FTX is 15.0. Okay, this last example is a little bit different. Okay, I have a beam with a mass of 20. Okay, and then an unknown mass, and it's going to be balanced. Okay, well, how can that be? I don't see anything on the right side. It turns out most of the mass of the beam is on the right side because I'm pivoted over here. We just have to figure out where to put that 20. And for something like this, you put the mass at the center of mass. Okay? And in this case, it's going to be in the middle of the beam. So I'm going to put right here in the very center of the beam, I'm going to put a mass 20 kilograms. That's going to give me a force there of 200 newtons. Now I can see why it balances. I have a force on this side of my pivot and a force on the right side of my pivot. Now, the force of gravity here, again, is going to be 10 M. So now I can go about finding the force. Okay, so I'm going to find the torque due to this guy. Torque equals F(r) sine theta. Force is 100. Now R is the distance from the pivot, so I have to be a little bit careful. I just said I put this in the middle of the beam. The whole beam is 1 meter, so this distance is 0.5 meters. And then since from here to here is 0.2, this has to be 0.3. So times 0.3. I don't have to worry about the sine theta because they're at right angles. So here I'm going to have the torque equals 60 newton meters. And that one is trying to make it turn clockwise. Now, I left out a piece of information here. We're going to say that this so over here, I can find torque is F(r) sine theta. Torque equals force is 10 M. The R is 1. So this is going to give me just that. Now set it equal. I get M equals 60. Now that I know that this mass is 60, I can say the force of gravity there is going to be 600. Now it also wants the force on the pivot in this case. This becomes a little bit easier because I don't have any X stuff. Everything is either straight up or straight down. So the force on the pivot is just going to be up that way. Alright? And when I do my Y forces cancel, I will get the force of the pivot going upward is equal 600 downward plus 200 downward. So 800